Today we're going to be talking about Half-Life. In class we've been talking about nuclear decay reactions, specifically, if we undergo alpha decay, we have that 4,2 helium that's emitted from the nucleus. If we undergo positron emission, we have a proton becoming a neutron emitting the positron. Uh, if we have electron capture, we have an electron making its way into the nucleus, kind of combining with a proton to become a neutron again. Those are all nuclear decay reactions, and really it occurs when an unstable nucleus, needs to emit a particle, emit some gamma radiation, absorb an electron, in order to become more stable. So one of the questions that we should have asked is, well, what determines when this atom does it? Because obviously, like if I have like carbon 14, it's existed for a certain amount of time and hasn't undergone this nuclear decay, even though it's been unstable the whole time. So this is where the idea of half-life comes into play. Really, what half-life is, besides being the title of a very popular, you know, PC game, it's actually really good. Half-life is how long it takes for 50% of the atoms of a radioactive isotope to decay, for them to undergo this kind of decay reaction. So essentially, like, let's say that I have uh, six six atoms of, we'll even say that it's carbon 14. And I know that when carbon 14, when it decays, it's going to undergo a beta emission to release an electron, and then the carbon nucleus becomes a 14,7 nitrogen nucleus. Okay, and we'll even say that the half-life um, half-life for this is something like 3,740 years. I don't think it's that, but I know I'm close. Okay. So then we might ask, uh, in 2 years, how much carbon 14 would be left? Okay. So half-life means in roughly 3,740 years, um, not 2 years, we're going to change that. In 3,740 years, half of my carbon atoms will have become nitrogens. Okay. And I'm just going to depict the carbon atoms here. And so let's say that in 7,480 years, how much carbon 14 is left? Okay. So first thing we might want to do is figure out how many half-lives have there been. So to do that pretty quickly, we just take how much time there is divided by how long a half-life is. In this case, um, we had two half-lives. So rather than saying that, we could say in two half-lives, how much carbon 14 is left? I know I've changed the question quite a bit here. All right. So in one half-life, doesn't even matter how we do it, let's say that we get rid of half of them. So half of 6 would be 3. So I'm down to 3 atoms of carbon 14 after one half-life. And after a second half-life, I'm going to get rid of half of these, and so that could either be just one atom. There's also a chance that a second atom goes as well. Um, or if I had, big thing though is you start with 100%. After one half-life, you're down to 50%. You know, after a second, so this would be one half-life. After a second half-life, we'd be down to half of the 50, which is 25%. After a third half-life, we'd be down to 12.5. The big thing is, though, is after each half-life, we've cut the number of atoms we're looking at in half. All right. So there is a mathematical formula we have over here that'll help us solve some of this stuff. All right. So we're kind of done with this stuff over here. All right. So I'm going to mess it all up. All right. So looking at this equation, let's actually start to identify what some of these things are. All right. So N is the final amount that could be mass. So we're talking grams. This could be atoms. It's just the final amount of our radioactive isotope. N0, that's our starting amount. And once again, that could be grams or atoms. Just know, like, if I'm starting with a talking about the amount in mass, I'm going to end with the amount in mass. Okay. 1/2 is literally 1/2. It's 0.5. It's just a number. It's always 1/2 because we're working with half-lives. Now this part might be a little bit trickier to see, but this little t here, oh, whoa, go ahead and undo that there. I see what happened. We'll be right there, okay. This t, this is how much time has passed. So that would have been the 7,480 years there. Um, T.5 or T 1/2 as you'll sometimes see it, that's the half-life. The half-life is unique for each isotope that is radioactive, okay? And for the most part, I'm always going to tell you what the half-life is in the questions I give you. There's also some charts you can find online. Half-life is kind of a constant. For the most part, if you're told what element and the mass of the element, you can go find what the half-life is for that element. Or if it's not known, chances are the questions are going to be asking you to find the half-life. All right, so with that in mind, let's actually take a look at this question kind of in practice. So let me go ahead and get rid of this junk here. So as I'm doing this, just kind of keep in mind, we talked about how it was how many atoms decreased each time. That's also going to be, like if I started with 100 grams of asbestos, after 1 half-life, I'm down to 50 grams. 2 half-lives, I'm down to 25 grams. It works for mass as well. All right, so my practice problem there at the bottom. The half-life of Zn71, of zinc 71, is 2.4 minutes. Okay, so right away, I already know the half-life. I know that my T.5 is equal to 2.4 minutes. Okay, so if one had 100 grams at the beginning, so it's implied it's 100 grams of the zinc 71, so I know my starting amount is 100 grams, or 100.0 grams. They want to know how many grams would be left, so we're looking for the final N, after 7.2 minutes had elapsed. Okay, so they're telling us that 7.2 minutes is how long we're going to wait for, okay? So to figure this one out, I'm solving for N, which is really nice because then starting off by itself, I don't need to rearrange anything. I know that N is going to be equal to the starting amount, which is 100 grams, times 1/2. In this case, I'm actually even going to make it 0.5. And I'm going to raise it to T, which is 7.2 minutes, over the half-life, which the question tells us the half-life is 2.4 minutes. I like to set it up this way. There are some places that will tell you, like, you can actually solve for this number first before you plug it in. But that doesn't help you if what you're looking for is T or T.5, which we'll go to here in a second, all right? So I've got 100 times 0.5 raised to the 7.2 over 2.4. Let's actually put that in parentheses as well. Really, I just need to make sure that I need to do the exponent, so the 0.5 raised to that power, before I take it times 100. And that's just PEMDAS. All right, so let's get out a calculator. Move that there. All right, so I've got 100. Let's even see if this is going to do it right. Times 0.5 raised to the parentheses 7.2 divided by 2.4, close parentheses, that's 3 half-lives right there, equals 12.5. So I'm going to end up with 12.5 grams, okay? Of the zinc 71. All right, and that makes sense. 7.2 divided by 2.4, that's 3. So we've got 3 half-lives. If I start with 100 grams, I read down to 12.5%, or in this case, 12.5 grams. Really, it's just plugging stuff in and just making sure you're doing the PEMDAS right, or PEMDAS, however it is you want to say it. So let's see. Sometimes they'll give you that number. Sometimes they won't. We're going to look at question number 4 there. Just because we're going to talk about kind of a new, kind of a math principle for some people. All right. I'm going to scroll down. Let me rewrite my base equation here. N equals N0 1/2 T over T 1/2 raised to that power. All right, so question 4. After 24 days, all right, so right away they're going to give us time. 24 days. 2 milligrams of an original 128 milligram sample remain. All right, so I know my starting amount just from reading that is 128 milligrams, and we ended with 2 milligrams. They want to know what the half-life of this thing is. All right, so now time for some new math. All right, so I need to get this t by itself. So sorry, t half by itself, which is in the exponent. So a lot of you might be thinking, how do I do that? Well, let's start by just plugging in what we know. So n 2 milligrams equals starting amount n0 128 milligrams times 0.5, and we're raising it to this power, which is t, 24 days over t 1/2 t 0.5. We could even, if that's a variable I'm looking for, I might even, if I'm going to do this super algebraically, I'm just going to call that x, okay? And that's my exponent up there, so let's just go ahead and pop that in parentheses. So if you haven't had Algebra 2 yet, or if you haven't gotten to this part in Algebra 2, our variable is up in an exponent. How do we solve for that? All right. Well, right now, it's 0.5 being raised to that exponent. Okay, this 128 is being multiplied by whatever that would end up to be. Let's start by getting the 0.5 to the exponent by itself. So to do that, divide both sides by 128 milligrams. I'm actually even going to do this math as I go. So the 128 milligrams cancels 128 milligrams. Let's go ahead and bring this over. So I've got 2 divided by 120. Might help if I typed it in right. 128.015625. I'm actually even going to leave it just like that. I don't want to do any rounding quite yet. 0.015625 equals 0.5 raised to 24 days divided by x. All right. So new math time. I need to figure out a way to get x out of the exponent up there. To do so, we're going to use something called logs. All right. So logarithms, I'm going to leave essentially your math teacher to kind of explain it. Really, if I'm looking at my calculator though, I can see that there is a log button right here. Just about all scientific calculators should have that. That's really what I'm looking. Really, it's a way of working with exponents. It's cool, it's fun, but here's what we need to do. Just like when I divided both sides by 128 milligrams to get the 0.5 to its exponents by itself, if I take the log of one side, might help if I wrote it right. Okay, if I take the log of one side, I can just take the log of the other side, okay? Pop these things into bigger parentheses. Actually, I don't want that last one. Okay, I'll do this one just because it's a decimal, okay? Here's the cool thing about logs, okay? Here's the new math. When you take the log of something raised to an exponent, this exponent, so really, like if I'm looking at I'm going to scroll down a little bit now. So if I have the log of 0.5 raised to the 24 days over x exponent. This exponent just comes down in front of that log, okay? So I'm going to have parentheses 24 days over x times the log of 0.5, and this is still equal to this right here. Log of 0.015625, okay? Now, my exponent's now in front. I'm actually able to do some math with it. So let's actually start. And like I said, you're just going to have to trust me that this math works. Some math teachers can explain it, or if you shoot me an email, shoot me a comment, I can take care of that. But in any case, I now can get this part by itself by dividing both sides by the log of 0.5 log of 0.5. Make that look a little bit better. Okay, there's actually some stuff you can do here. But the big thing though is now I have 24D. Scroll down here. I've got the log of 0.015625 over the log of 0.5 is equal to 24 days over x. Essentially at this point, you could multiply both sides by x. Essentially, you're just going to cross multiply to get this thing solved. X's cancel out, and then we can also times both sides by the log of 0.5. That cancels that, times the log of 0.5. And now I can divide both sides by the log of 0.015625. Make sure I don't get that confused with anything. This is being divided by the log. And this is just algebra at this point. 625. All right, let's actually try to plug this in to see if I can get a reasonable answer for x here. All right, so let's also see how good my calculator is at this. I want this here. All right, so I've got 24 times the log. Okay, I see what's going on here. Clear that out. So let's even start. So 0.5 log. No, let's completely cancel. 0.5 log divided by 0.015625 log times 24. And I get nice even 4. Okay. So all that math, all that algebra, just to find out that the half-life for whatever this sample is 4. My time was in days, 4 days. Okay. And really do that. The new math trick we had to do is if you take the log of one side, you take the log of the other, and that allows you to move your exponent down in front of the log. And then after that, it's just back to basic algebra that we've done before. I know this is a long video, it's a long explanation. Half-Life, the math is actually pretty easy. The theory behind all the log stuff is kind of its own separate thing. But if you just know those log tricks, you don't even have to understand the log tricks. If you can do them, you can do Half-Life problems. All right, so with that, good luck with the practice.